Good evening, everybody. It's Friday, the 31st of March. Sorry, it's Tuesday, the 31st of March. And this is Nighttime Mathematics Radio. The show always has the same format. You tweet your questions to me at Night Math Radio on Twitter, and I'll try to answer them right here on the air. So we've got one question that came in over the week, which I'll try to use after the break. But first, let's take a little break to let people on Twitter tweet their questions in. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, we got one question over the break, and I have to apologize for the break being longer than extended. We had some equipment problems yesterday, which kept us from streaming, but we are back on the air tonight. And the question that came in looks at this problem. It starts with a pretty typical problem. It says the rate at which an air conditioning unit for theater complex pumps out cool air in metric tons per hour is given by the differentiable function r of time. The table shows the rate measured every hour over an 8-hour time period. So here we have our table, which says, okay, let's look at t in hours, which will measure 0, 1, 2, 3, 4, 5, 6, 7, and 8. And then we have our rate in metric tons per hour. Oops, this thing's a little too zoomed in. I can't really see what I'm doing, so let me zoom out a little bit. A little more zoomed out than that. There we go. There we go. Come on, focus, you silly bit. There we go. This time we're focused. And we're given that 0, it's 4.6. At 1, it's 5.4. 2, it's 6.1. 3, it's 6.5. 4, it's 6.8. 5, it's 6.3. 6 is 6.0, 7 it's 5.5, and 8 it's 4.8. And so you might well look at this and say, wait a minute. We spent all this time with fundamental theorem of calculus learning that an integral is the opposite of a derivative. It's an antiderivative. And we spent all this time learning integration trick after integration trick after integration trick. What is this? how can I integrate this mess of numbers? And the answer is, in real life, you're usually integrating a mess of numbers. It turns out this is the fundamental difference between differentiation and integration. If I give you a function that's differentiable, you can find its derivative. There's no question. And its derivative will have a closed form. You can write down its derivative in terms of other functions you already know. That is not true of integration. If I write down a random function, even in the one using nice functions, sines and exponentials and polynomials and stuff you've known from the beginning of time, unless you get really lucky, and of course, in calculus courses, we're dedicated to making you really lucky, and when you're doing your own research, you often contrive yourself to make yourself really lucky, because after all, if you're going to make a model, you might as well make it one you can integrate. But in real life, if you're just getting data, it's not going to be integrable. If I write a random function down, it's not going to be integrable. You have to do it numerically. And that's what this problem's all about. So the first problem says, use a midpoint Riemann sum. With 4 intervals to approximate the integral from 0 to 8 r of t dt. See, this is the thing we would like to integrate. But of course we can't. We just have a bunch of numbers. We only have a functional form. We have no reason to believe that it's integrable to closed form. So how does this work? Well, 4 intervals means 0 to 2, 2 to 4, 4 to 6, 6 to 8. Midpoint means you use the midpoints of each interval. So use 1, 3, 5, and 7 as our values. And we just write this thing as a sum, as if we were just drawing rectangles up to the middle of each interval. So what is that? Well, it's the sum of 4 intervals. So it's a sum of, the first interval is 2 hours long. In fact, every interval is 2 hours long. We're going 0 to 2, 2 to 4, 4 to 6, 6 to 8. Times 5.4 metric tons per hour plus 2 hours times, now we're doing 3, 6.5 metric tons per hour plus 2 hours times, now we're at 5, 6.3 metric tons plus, last but not least, 2 hours times 5.5 metric tons per hour. So we've got 4 terms. What are the units of each term? Well, it's hours times metric tons per hour, so the hours cancel, you end up with metric tons. So every term has metric tons, which is good, because you can't sum numbers that are different units. It doesn't make any sense. You have to convert everything to the same unit first, and in this case we don't have to, which is great. And if your units are fundamentally different types of unit, that is, you can't, if you have, say, 6 pounds plus 3 inches, for example, that means you must have made a mistake in getting your formula. That's always a really good check to make sure that your formula is at least plausible. Now, we can just evaluate this. That's 10.8 metric tons plus 13 metric tons plus 12.6 metric tons, last but not least, plus 11 metric tons. So 13 plus 11 is 24. That's 34.8. Then we add the 12, so it's 34.8 plus 12.6, which is 47.4 metric tons. And then, because I can do this in my head because I'm not turning this in, but you should probably double check. So let's just make sure that I got that right. 10.8 plus 13 plus 12.6 plus 11, 47.4 metric tons. Great. Easy enough. Question B is actually, it's just sort of fun. It says, is there some t sometime t, somewhere between 0 and 8, where the first derivative is 0. And the answer is, well, fortunately, we were told that this function is differentiable, and this is why. Because we see that the function is increasing here. Between 0 and 4, the function is increasing, which means we know by the mean value theorem that there's some point between 0 and 4 where the derivative is positive. Because after all, and notice you can't just say it's positive for that entire interval, because we don't know any of the points in the middle. For all we know, it's wiggling like crazy. It just happens to be higher each time we get to an integer. But we can certainly say by the mean value theorem that somewhere between 0 and 4, it takes a value of 6.8 metric tons per hour minus 4.6 metric tons per hour divided by 4. So we know somewhere in that region that the derivative of the thing must be positive. And by the same logic, we know it must be negative somewhere between 4 and 8. Again, using mean value theorem. So since it's negative at some point, it's positive at another point, we're told that it's differentiable everywhere, which means it's continuously differentiable, because otherwise it's not differentiable everywhere if there's a point. So if there's a point where the derivative is missing. So since it's differentiable everywhere, there must be a point where it goes through 0. After all, if it's positive here or negative there, and it's continuous, it's got to be 0 somewhere. Finally, we're told you can approximate the rate of airflow using a polynomial. And they write down the polynomial. I'll put that on the next page. They say, okay, whatever R of t is, it's close to Q of t, which is 1/8 36 plus 8t minus t squared. And I mentioned way back in another video, I mentioned this is the main use of quadratics. Is a quadratic's the simplest function which goes up for a while, then goes down, or goes down for a while, then goes up. And the one thing we know about this is it goes up for a while, then goes down. So about the simplest function we could throw in there is a nice quadratic, and here's a nice quadratic. It said, use Q of t to approximate the average airflow during the 4-hour period. Well, what is the average airflow? Well, we have the airflow as a function of time. So we know the total airflow must be equal to, or approximately equal to, the integral from 0 to 8 Q of t dt. And that will be in metric tons, because we've just integrated something that's in metric tons per hour times hours. So if we're on average, we have to divide by the length of the interval, which is 8 hours long. So how do we do this? Well, this is just a nice simple polynomial, right? This is... And you know, I'm going to stop running units at this point because they were obnoxious and didn't write units in their thing. Shame, shame, shame. After all, that first 36 should be 36 metric tons per hour. The 8 should be 8 metric tons per hour squared, so that when you multiply it by hours, you get back metric tons per hour. And t squared, and that 1 there must be times metric tons per square hour, per hour squared. So that when you multiply it by the hours squared, you get back metric tons. But they were obnoxious, and since they were obnoxious, I'll be equally obnoxious and just write 1/8. So this is 1/8 times the integral from 0 to 8. 1/8 times plus dt. And now we're going to use the nice properties of integrals that you can pull constants out of the integral and you can split them at sums and differences to just write this down very simply as 1/64 times 36 times the integral from 0 to 8 dt plus 1/64 times 8 times the integral from 0 to 8 t dt minus 1/64 the integral from 0 to 8 t squared dt. And we can simplify these, of course. (36 over 64 is just 9 over 16. It's 9/16. The integral from 0 to the integral of 1 is just t, so it's t from 0 to 8 plus 1/8 t squared over 2 from 0 to 8 minus 1/64 t cubed over 3 from 0 to 8. So we can start simplifying. This is obviously just 8. 8 cancels 60 to give us 6, so that's 9 halves. Plus, that's 64 over 16. Or right, because 2 times 8 is 16. 8 squared is 64. One of the 8's cancels, so that's 8 over 2, or 4. Minus 1 over 64 times 3, t cubed, which is 64 times 8, which I don't feel like figuring out in my head, but 64 times 8 is actually useful. So it lets me cancel 64ths. So that's 9 quarters plus 8 quarters, which is 17 quarters. Sorry, 9 halves plus 4, which is 17 halves, minus 8 thirds. We can dig a bit into our fraction math here. That's 51 sixths minus 16 sixths. Sixths is a very difficult thing to say, as it turns out, especially when you're teaching. It was the bane of my existence when I was teaching, because it's very difficult in front of a classroom to say sixths in a way that doesn't sound ridiculous. So our answer will be in sixths. That's 41 sixths minus 6, which is 45 sixths. Oops, losing my mind. 35 sixths. Thank you, that makes more sense. Doing math in your head is not always the best thing when you're tired. That's 35 sixths. And remember, it's always better if you can to give your answers in human terms. So what is that? Well, 6 times 5 is 30, so this is 5 and 5 sixths. And what units is it in? Well, this has to be, again, this is the average rate of airflow, so this is, again, in metric tons per hour. And that makes sense looking at our graph. Our graph starts about 4.6 or below this number. It swings up to 6.8 or well above this number. This number is sort of in the middle somewhere, which makes perfect sense. This is a very basic form of something that's called quadrature. Quadrature is numerical integration. It's figuring out what an integral is from a bunch of numbers. Midpoint Riemann sum is one of the simplest ones you could do. It works well enough for this problem. There are others you could do if you want to be fancier or get a more accurate picture. In this case, it would make sense to do something a little more sensible, because after all, we know more data. In this case, we threw away a lot of data using a 4 subinterval thing. It would make more sense to use 8 or 9 subintervals, because we have 9 data points. But this is decent enough. This is Nighttime Mathematics Radio. Let's take one more break to see if anybody else dials in before the break is over, and if not, we'll call this a night. Well, everybody, we've got no new questions on Twitter. It's getting late. I think it's time to call this show to a close. So everybody, as you sit in your homes where the classes have stopped, but the homework goes on and on and on, just keep tweeting your questions here to Night Math Radio at Twitter. I'll try to answer them live on the air. Good night, everybody, and stay safe. See y'all tomorrow.